right, maybe we can get started. And yeah, I guess for today you can kind of see an overview of what we're going to talk about. I've got this sort of lecture slide up here because there will be a little bit of lecture stuff at the beginning. We're going to talk about diffusion for the lesson this week and look at some examples of different ways in which diffusion occurs in nature, focusing mainly on erosional processes because that's an easy thing to sort of simulate as a diffusion process. But before we do that, I wanted to ask if there were any questions about this exercise number 2 that you wanted to ask at this point. Yeah.
How would it work when you weigh in the standard deviation?
Yeah, so if you want to do a weighted regression, I don't know offhand mathematically how that is different, but essentially the smaller the standard deviation is, usually you apply a weight factor that is proportional to 1 over the standard deviation or 1 over the standard deviation squared. So as that value gets smaller and smaller, this weight gets bigger, and then that pulls the line to fit those points with a small standard deviation more closely. I could probably find a decent reference for that, but I don't know offhand kind of how that's formulated in terms of what we looked at for this least squares regression. But were there other questions for exercise number 2? How did it go overall? Was it okay? Mostly? If it was not okay, is it like mainly Python problems, or is it other things that are confusing? The equations, or anything in particular that was difficult to deal with? Because I could try to focus a little bit more on some of those things if I have a sense. But okay. Well, maybe I will try to get a little bit of feedback in other ways about how these exercises are going at some point. But yeah, if there's not any other questions about this exercise 2, we can move on to the lecture topic for today about natural examples of diffusion. And essentially there's 2 things that I'm going to try to do here with some introductory slides. First is just to introduce the diffusion process in general, and then to give some examples of different erosional processes that can be simulated as a diffusion process, and that would be modeled using the diffusion equation. So there's a lot of different examples. Here's just 3 possibilities for diffusion as a geological process, and they relate to different kinds of things. So rock rheology, when you look at the process of grain boundary sliding, it's one way in which crystals deform inside of a material, and essentially at a large scale it operates like a diffusion process. There are other things like diffusion of noble gases inside minerals, so argon or helium that's trapped inside crystals basically undergoes diffusion in terms of its movement and the movement of the atoms in the crystal. Generally speaking, the concentration of these atoms is greater inside the crystal than out, so the tendency is that these natural gases will gradually diffuse out of the crystal over time. And that has applications to thermal chronology, which we'll come back to at the end of this course. The other example that we'll focus on for today is hillslopes and the way in which hillslopes erode. And rain splash is perhaps not something you really often think of when you think of the ways in which hillslopes are eroding, but when rain strikes the surface, it can displace sediment grains on the surface, and the movement of those sediment grains downhill, generally downhill, is a process we can model as a diffusion process. So there's lots of different other examples I could include, but these are just a few to get us started. A big part of what I'm going to focus on for the lecture part of the lesson today is to kind of give you an idea of what the diffusion process is and how we define it mathematically. And this is one of the ways in which I hope to see the course help you, and that is to be able to translate equations and math sort of descriptions into something that you can play around with in Python. So when we talk about diffusion, we're basically talking about a process that results in either mixing or mass transport as a result of random motion of diffusing particles. So we could do a demonstration with this if you'd like, but you might have to get up and move a little bit closer to one another just for a moment so that we can do this. So what we saw is that we randomly moved things around, and we basically simulated something kind of like what's in this animation here, which has a concentration in this case of some atom A on the left and atom B on the right. And this is sort of like our green and red eggs. And then what's plotted on the bottom is the concentration of A as a function of the distance across this kind of model here. And when you start running this little model forward in time, what you see is that basically by random exchange of atoms at the initial interface, you start to smooth out what was initially a very strong gradient between the two different types of blue and yellow atoms in this case. And you can see then that the concentration of A starts out as basically a step function, so very sharp, and then gradually gets smoother and smoother over time. So this is one of the things that's kind of key to a process that we could consider to be a diffusion process, is that concentration gradient is going to go down over time as diffusion is happening. So the general idea here is this mixing as a result of random movements. The net motion tends to be from areas of high concentration to low concentration. So if we had a high concentration of green eggs up here to start with, they moved out in the direction away from where that high concentration was. If it was a concentration of thermal energy, like something that's hot things will cool, and you'll have energy transferred from high to low concentration of heat. And it reduces gradients. And so we saw that in the animation and in the little demonstration as well. If we want to get to a little bit more quantitative definition, we can say that diffusion occurs when a conservative property moves through space at a rate proportional to a gradient. This is probably one of the more confusing sentences that I could put on the screen right now, so we're going to go through this kind of piece by piece, because unfortunately if you look up the definition of diffusion, this is the kind of thing you're going to read, and it would then fall on you to figure out what that actually means. But there's a few things we can highlight here to start with. One is this conservative property, which is just some property that must be conserved in the system, so whether that's mass or energy, momentum, whatever it is. And then this rate proportional to a gradient, which means that the movement of this heat or atoms or eggs or whatever occurs in direct relationship to the change in concentration. So the steeper the concentration gradient is, the faster the material will tend to diffuse at that boundary. And if you think of an example of something like a hot, piece of metal that you put in contact with a cold piece of metal, the change in temperature is going to be greatest at the interface between the two at the start of the process. So here's our definition. This kind of nasty thing. If we take this rate proportional to a gradient part, we can translate this into some kind of mathematical definition here by just saying that, okay, well, what this says is the transportation rate is proportional to the change in concentration over some distance. That's just another word for gradient in this case. And I think that's kind of not so bad to deal with. If we put it in a little bit more quantitative terms, we could change transportation rate to be something called the flux. Those two things are more or less the same. So it's the rate at which material is being moved or things are being heated up or whatever. is proportional to this concentration gradient. And we saw that in that little animation before, where the concentration gradient was high, we saw the greatest change in concentration at the start. And if all we do is just replace this with mathematical symbols, we end up with something that looks like this. We'll call the flux Q. That's often the letter that's used for flux. Here we'll call it mass flux, since we're, in this case, talking about these two different concentrations of atoms. This little alpha-like symbol is the proportional to symbol, and then this concentration gradient, just the change in concentration over some change in horizontal distance x. So delta C divided by delta x. So that's not so bad, and that's one part of our diffusion equation. This thing might look familiar over here. I guess it doesn't start animating till the next slide, but when it comes to writing out the more general form of the diffusion equation, these capital delta symbols that are indicating some change in concentration or change in distance are replaced by an infinitesimal change. That just means that as you go to smaller and smaller distances, you can represent this kind of tiny infinitesimal distance with a small delta. A capital delta would represent a kind of discrete distance or concentration change. So this more or less looks the same, and we have Q, and then instead of having it be proportional to something, we can substitute out and put in a constant there called D, the diffusion coefficient or diffusivity. So now we can say that this flux is equal to this coefficient of diffusion times the change in concentration divided by the change in distance. So that's, yeah, maybe not super exciting, but if you're confused about this at some point and you want to go back and try to understand where this equation comes from, essentially this is where it's spelled out, and you're welcome to look at the lecture slides to have a look there. The key thing at this point is that we have some flux that's now equal to some constant of diffusion times this concentration gradient. And again, like we saw in the animation before, the places where that concentration gradient is largest are the places where you see the change in concentration happen the fastest. So if you're way out here at the edge, you have all blue atoms over here on the left side, and basically nothing happens to the concentration over here through time because there is no gradient. It's all blue atoms over on this left side. And if we allowed this thing to run for longer and longer, eventually you'd start having some concentration gradient here, as well as some of the yellow atoms would start moving to the left. But that gradient's still going to be pretty low, and the concentration on the left side is going to change quite slowly as a result. In the middle, where this is basically a step function, you can see the concentration of atoms of A rapidly dropping off on the left side and rapidly increasing on the right side of this line dividing the two at the beginning. So that's essentially just what this equation is showing us. So there's an interesting question here, or, well, I don't know, interesting perhaps depends on your perspective on life, but why is there a minus sign for this equation? Yeah. Yeah. Is that your answer, or is that a, yeah. So, yeah, in this case, like, what we're seeing is the concentration of A over some distance x. And we could look at this by just looking at two different points here on either side of this concentration line. You could take them right next to each other, but we'll just take them here, where we've got some concentration C1 with the red dot and concentration C2 with the blue dot, and then x1 and x2 as the position of those 2 points. If we took this equation and just put it in terms of like a finite difference, delta C, we could say C2 minus C1 divided by C2, or so x2 minus x1 is this concentration gradient. So if we look here, C2 minus C1, is that going to be positive or negative? Yeah, right. C2 is small, C1 is big, so small thing minus big is going to give a negative number. And then x2 minus x1, positive or negative? Positive, right? So we're going to have a negative number divided by a positive number, so this term is going to be negative. And there's also this minus d out in front here for the diffusion coefficient, so we multiply a negative number by another negative number, you're going to get something positive for the flux. In other words, in the x direction, the flux of atoms of A is positive. But at any given point along here, we're seeing a decrease in the concentration of atoms of A at some fixed point here. But relative to this region over here in B, or basically anywhere along here, we're going to see that atoms of A are moving to the right through time. So that gives us a flux of mass in the positive x direction. So yeah, exactly, this minus sign comes out of the fact that we're looking at the concentration of A. If we were looking at concentration of B, the same equation would apply, but then the direction of x might be different, and so we might end up with a negative flux in that scenario. But what you can see here basically is with the arrow, this positive flux of atoms A in this picture. Okay, so we've dealt with the first part here about this rate proportional to the gradient. The second part, this conservative property moving through space thing, is a little bit less obvious to understand, but we can still, I think, do it and do reasonably well. Here, what we have to say is that this change in concentration with time is what we're going to call our conservative property. So if we're conserving mass, the change in mass with time is equal to the change in transport rate with distance. So this has something to do with this concentration gradient and the fact that it may change as you move from one place to another. So first part of what we talked about, this rate proportional to a gradient, is a key part of a diffusion process. The diffusion equation is essentially a way in which we can conserve mass, and that's where this other part of the definition comes in. Oops. So again, we're just swapping out the things in red here. So this change in concentration with time, we can just call that the rate of change of the concentration. That's, again, just saying basically the same thing, but this is getting to be a little bit more like a mathematical definition. And the change in transport rate with distance, well, the transport rate is the flux, and so its change with distance is basically just a flux gradient, which is a little bit weird to think of maybe, but hopefully that'll make sense in a minute or two. So if we just change this again like we did before into mathematical symbols, the change in concentration with time, or the rate of change of the concentration, is just delta C over delta T. That's not so bad. And this flux gradient is just the change in flux, Q, we saw Q before, divided by delta X. So that's the change in flux over some horizontal distance. Those are the pieces. This is basically a conservation of mass or conservation of energy equation in the way that it's written here, and don't want to take the time to go into exactly how that all works right now, but it does conserve mass or energy when you apply this equation. Well, how does that go? Well, we can look at it just in terms of general terms first, and that is to consider some fluxes, Q1 and Q2, at two different points, x1 and x2. What's going to happen here if the flux of mass at Q2, flux of mass Q2 at x2 is greater than the flux at x1 here as Q1. So let's say Q2 is bigger than Q1. And again, we'll assume that x2 is larger than x1. So if Q2 is bigger than Q1, this top term is going to be positive or negative? Positive, right? X1 minus x2 is going to be positive again. So we have a negative sign out in front of here. Both these things are positive, so this should mean that the concentration goes down with time. So if there's more mass being fluxed away at some point than there is mass coming into that point, the concentration should go down, and that's exactly what this equation says. So if these fluxes are out of balance, then the concentration changes. If the fluxes are exactly equal to one another, Q2 minus Q1 would be 0, and the concentration doesn't change. So if you think about this in terms of, some flux of atoms, if the number of atoms coming into some location is equal to the number that are going out, then essentially you don't see any change in the concentration. So if these two fluxes are equal, it says that for a diffusion process, the concentration wouldn't change. And that's essentially how this works as a conservation of mass equation. If the fluxes are out of balance, then we see the concentration go up or the concentration go down with time. Again, you could look at this in terms of this example here of simple animation of diffusion. I'm not going to spend any time on that right now because I'd like to get to some other things, but I'll just put in a sort of plug here that one of the parts of the lesson for this week that's on the web page but that we're not going to go through in much detail is solving the diffusion equation. So if you want to see how this sort of two equations that we've looked at come together and result in the diffusion equation that you'll use for the exercise this week, that's all available on the course page. It's not that complicated, but it's also not very interesting. So at least not very interesting to sort of present in this form. So I'm going to leave that as something that you can have a look at yourselves. But for the remaining part of this sort of quick introduction to diffusion, we're going to talk about one specific type of diffusion process, and that's Hillslope diffusion. And so this is one way in which mass is transported at the Earth's surface. So you could consider this like an erosional process or some kind of process that changes the shape of the Earth's surface. And there's a number of different individual Hillslope processes that all operate in a diffusion-like manner, meaning that we can model them over long time scales as basically being diffusion processes, even though over short time scales they might not strike you as diffusion-like. To talk about this, though, we have to just briefly say something about the way in which erosion happens on the Earth's surface. I don't know if any of you have had a course in geomorphology, but I guess probably not. So there's basically two different kind of length scales that we use when we talk about erosional processes. There's long-range erosional transport processes like rivers that transport material hundreds of kilometers. Glaciers could potentially be considered one of these long-range transport processes. And then there's things that are often classified as short-range, which means that it's more or less happening on hill slopes. So the spatial scales could be, up to maybe 5 or 10 kilometer distance total. In a picture like this, I mean, of course, the rivers are flowing very large distances. This is somewhere in the central Himalaya. Hillslope processes are basically things that are happening from the ridge crest here down to the river valley as one example. And so they're much shorter distance associated with those. Now, this is not a course on geomorphology, so we're not going to go into all of these different hillslope processes. There's lots of different things that happen to erode the Earth's surface on hillslopes. Slides, landslides, I'm sure, are something that are at least somewhat familiar, and maybe you're also familiar with certain things like mud flows and other kinds of mass movements on hill slopes. We're going to focus on the one that's probably the least exciting, at least in terms of like a day-to-day process, and that is things related to heave. And I'll show you a few examples of what those look like. But basically, these are things that result from expansion of material near the Earth's surface and its movement as a result. In terms of this little diagram showing different kinds of mass movements, slides are down here on the left where they're more or less dry. You can have rock slides and things like that where there's essentially very little moisture involved. It's just kind of dry rock falling. Landslides might have a little bit of more moisture. And then things like flows are really flowing more like a proper fluid. We're over here in the heave corner in this sort of slow processes that are important, but maybe not so exciting to sort of sit and watch. So creep is one of these kind of things. So it's a very slow movement of material at the Earth's surface in response to gravity. And I'll show you a couple pictures here that might look somewhat familiar. The heave part of this creep process is just the vertical movement of material as a result of expansion and contraction, which could be freeze and thaw cycles for water, or just saturation of soil and then loss of moisture and things contracting. And if we look here, we can see kind of one example of this heave process. So here we've got vertical shale beds, and you can see as they come close to the Earth's surface, this is like I think it might be a road cut, but some kind of vertically exposed surface. And you can see as you go up near the Earth's surface that the orientation of the bedding changes. Things kind of rotate and tip down slope. And this is more or less happening as a result of seasonal creep. So this rock here is gradually kind of moving down the slope slowly as a result of this creep process. There's other examples, perhaps things that you've even seen if you've been out in the sort of woods somewhere and seen any kind of soil mantled hillslope. You'll often see trees that have this kind of bend in the trunk like this. I guess maybe you've seen this. That essentially happens as a result of this heave and creep process, that as the soil moves downhill, basically the tree's roots are being taken downhill with it, and of course the tree wants to keep growing up. So as things kind of move down, the tree gets the bend in its trunk. This can happen also from snowfall. If you're in a place where there's quite a lot of snowfall, there's a kind of snow pressure that can bend trees. But this can happen in places where there is no snow, and you've probably seen this in places before. And here's another example of a telephone pole that's been sort of tipped over by the creep process. Here's the picture of how it works on kind of a small scale. So if we're near the Earth's surface here, within the region where this creep and heave process is active, essentially what happens is there are times when either you might have some swelling or freezing that results in expansion of material near the surface. The expansion basically happens nearly perpendicular to the Earth's surface, and so this vector E would show, some movement of soil or sediment as a result of expansion up perpendicular to the Earth's surface. At some later time, when things thaw or the swelling is reduced, you would expect that gravity is going to cause that sediment particle to go vertically straight back down. So rather than moving back perpendicular to the Earth's surface, it follows a different trajectory and it moves down under the force of gravity, at least in theory. So what happens in nature, of course, is that things don't quite follow this vertical path up and down. But the point is that as you go and expand and contract and expand and contract, you're going to follow this sort of sawtooth pattern and end up with mass moving downhill quite slowly. So what kind of things do you think might be important in terms of a process like this, in terms of the rate of mass moving downhill? What types of things would?
Yeah, the mineralogy, if it's like clay minerals, or how it's if you have a layer of clay somewhere as an unpermeable layer that can get the water in, and it can be that the whole landslide starts flowing.
Yeah, I mean, there's a couple things there. Like, one, if you've got a lot of clay minerals in the soil, they expand quite a lot when they get saturated. That could be quite important. Is there another?
Yeah, I was going to say the rate of expansion.
Yeah, right. So how much it expands, really. The rate of expansion maybe is not so much as important as like just the total amount of expansion. The more it expands, the more potential you have to move further down the slope. There's one other thing that's kind of important in this process that might be worth considering. It's not necessarily a geological. Yeah, exactly. Right. The steeper the hill slope is, if you make this thing expand, from a very steep hill slope, it goes out on some angle that's quite shallow. And then when it comes to the vertical movement back down, it's going to go quite a long distance to get back down to where it was. So exactly, that hill slope angle is probably one of the more important things just in general. The steeper the slope is, the faster this material should move down slope. Now, of course, there's limits to this in reality. That creep is not going to occur on a 45-degree slope because it's probably going to fail by landsliding. It's too steep at that stage. But, you know, as you go up to maybe 20 degrees or something like that, more or less the steeper the slope is, the faster the process happens. So, yeah, it's strongly dependent on the hill slope angle and exactly what I just said. This is the flux being proportional to the topographic gradient, or flux being proportional to the gradient part of the story. Steeper the slope is, steeper the topography is, the faster the flux of material is. And so this is why we can model this as a diffusion process, because rates of creep more or less depend on the slope of the surface or the gradient in the Earth's surface. So, yeah, I think I'm going to skip over these questions because we kind of don't need to talk about them. But I will say I'll put this up with a few extra slides at the end in case you're interested. I've had this be longer in the past, and it's not really necessarily been beneficial to be longer. But if you're interested, there are other processes that happen as diffusion processes. If you want to see a few others, like solifluction happens in kind of periglacial areas where there's melting and then material flowing down the surface and then freezing again. But there's also some interesting stuff about rain splash. It's kind of a fun geomorphic process, and I threw in a few slides from some article I found looking at experimental rain splash, where they basically put sand grains on different angle slopes and let water drip onto it and see how do the individual sand grains move through time, get a sense of the movement of material downslope. And you see essentially as the slope gets steeper, more and more material is being displaced down the slope, even though when the rain, I think they use some kind of like terminology that makes it sound like a meteor striking the earth or something, bolide impact or whatever, but the raindrops hitting this dry sand basically scatter sand in all directions away from where it strikes. But if you're on a slope, more of that material goes downhill than goes uphill. So that's how that goes. There's other things like tree throw. When trees tip over, they tend to throw more dirt downhill than uphill. And when gophers dig holes, so geomorphologists study all these different kinds of processes. If you're in places where there's a lot of gophers or other kind of animals that are digging in the ground, it tends to be the case that they don't like to put the dirt uphill. They dig more so that the dirt goes downhill, and as a result, you get mass moving downhill. And in some places, that's actually significant. So anyway, the slides will be up on the course page. I think they're not, the link probably doesn't work yet, but I'll put them up shortly. So, okay, then let's come back here just for a quick overview of the lesson 3. We've just seen the slides on natural diffusion. As I mentioned, there are these notes on solving the diffusion equation. If you click that link in the lesson materials, it is marked as optional. But if you want to see the equations that we looked at here, we had this concentration gradient equation that we can put in slightly different form here. We had our mass conservation equation that looks like this when we talk about hill slopes. And you can put those two things together to come up with a kind of classic diffusion equation that looks like this. And then we can solve that for different boundary conditions, and you end up with some equation for finding the elevation of the Earth's surface, in this case called h. And this is the equation you're going to use in the exercise today, this bottom one. I don't think I can highlight just that bottom equation. But anyway, that's the equation we're going to use for the exercise today, that just calculates a hill slope profile using a diffusion equation. Which brings us then here to today's exercise. So like the weeks before, we've got a starter notebook. The exercise is out of 10 points. But here, problems 1 and 2 are both in the same notebook. you're going to create a function in problem 1 that you also use in problem 2, and I thought it was just easier to keep it in one notebook than to have you copy and paste the function over from the first to the second. But I can just give you a quick overview of the two problems, and then you're welcome to get started. The first one is essentially where we kind of set things up. We're going to calculate these diffusion or diffusive Hillslope profiles, and maybe I'll just draw a quick thing on the board just to kind of show the picture of a few things that are important. So we're going to call this axis H because we're going to deal with height, and then this is the x-axis along here like normal. What we're going to be looking at are Hillslope profiles that look like something like this. And the idea is that this is like a cross section through a hillslope. So there would be some river down here, some river down here, and the region within here is being uplifted. The assumption here is that the river elevation is not changing with time, and so if you fix the points of the river and you uplift the landscape, everything here is going to move up. And you can see here that, like, as a result of this shape, there would be a tendency for mass to move down, like we just saw with these diffusion processes. We're looking at a steady state case with the equation that we're dealing with. So we're not looking at the formation of this thing where, you know, maybe it grows up to reaching this shape, but rather just the kind of stable geometry of if we have some rate of uplift and some fixed elevation of the rivers, we can calculate how high would this region get. How much would this surface be uplifted if we have diffusion transporting material down toward the rivers in reality here. So yeah, so this u, you'll see that in the equation, that's going to be the rate of uplift of the landscape. As I mentioned, the rivers are fixed. The way that the system, the sort of geometry of the problem, is that the rivers are at x equals L and x equals negative L in terms of the equation. So in other words, the highest point of the topography is at x equals 0 in the center of the model region here. You'll see this thing, this part of the landscape here, referred to as interfluve. It's just the land that's between two adjacent rivers, just a kind of geomorphological term for this thing. So I call that the interfluve in the exercise, so if you get confused about what that means, it's just referring to this uplifted landscape between the rivers. Otherwise, you're going to have some diffusion parameters that you're going to play around with, and yeah, you'll define some range of values of x, and you're going to calculate how high the landscape should be using this equation that's given in the exercise as well as in the notes on solving the diffusion equation. So that's the picture of what we're working with. So you'll have a few different tasks in here, of course. Your first one is going to be to define a Hillslope profile function, which essentially means you're going to translate this thing into a function in Python, this equation, and I think by now that's hopefully getting a little bit more familiar. Oops, I've got typos here with some unknown characters, so I've got to fix that one. Actually, probably that's, well, whatever. So yeah, that's our equation. So you'll start out by making a function called Hillslope diffusion. As I mentioned in the exercise session last time, please use the same variable names and things like that that are listed here. So you know, use L for this width or half width of the interfluve, and X for the distance along the model, U for the uplift rate, things like that. And you can do this with a for loop if you want, or you don't necessarily need to. So I'll let that be up to you. The kind of preferred NumPy way to do this would be not to use a for loop, but it's perfectly fine to use a for loop if you like to do things that way. And yeah, like always, once you've defined your Hillslope diffusion function, you should be able to test it with the code here, and it should give you the value that's expected. So that's how you can check and see if your equation is working properly. After that, you're going to calculate the geometry of some Hillslope. So you're just going to plug in some numbers to your equation, and you'll get some values for the Hillslope. You can store that as a variable called h, and then at that point you can make a plot of the shape of the Hillslope, and you should end up with something that looks like this. After you do that, then we can play around with how the model works, and we'll do that by just changing some of the different variables in here. So if you make the interfluve half width L twice as big, you can see how that changes the shape of the Hillslope. If you double the uplift rate or double the diffusivity, you can see how those things affect the Hillslope, and as well as reducing the diffusivity by half. There's going to be some text that you'll put on the plots to show things like the slope angles and things like that as part of this part 3. So with that on there, then when you get to part 4, you'll see that some of these variables will change. The elevation might go up by a factor of 2 and other things like that. So you'll make 4 plots here. Each one has its own little cell that you can put your plotting stuff into. For problem number 2, we're basically going to take what we did in problem 1 and apply it to kind of a natural system. So I'll go to a much bigger spatial scale. The first one, I think it's like 100 meters scale, and so that's not really comparable to the distance between rivers in nature. So we're going to go in part 1 of this to just looking at kind of a bigger system, and in part 2 we're going to go to the western part of the United States, to the Sierra Nevada mountains in California. And there we have this topographic profile between 2 rivers here, and that looks like this shape here. You might already notice that the shape of this thing looks sort of like the geometry of what we're calculating. And the idea is to calculate what the rate of uplift would be that would give you the shape of your model Hillslope that looks close to the shape of the Hillslope here in this elevation profile. So you're going to load in a data file that has this elevation profile data, and you're going to plot that together with your prediction of the Hillslope geometry and play around with the values of uplift until you get a good match between the two. We could make this more quantitative and actually put like a misfit function in there to calculate with a number how well we fit the data, but in this case we're just going to say visually the curve that you predict with your code and this observed topographic profile should look similar. So the elevation of the top of the profile should be comparable, and the sort of general shape should be comparable. That's basically it then for problem number 2. There's a couple questions at the end, but you're using the same equation, same function that you do in problem number 1. So I think that's probably where most of the work is going to go, is just getting that function working and setting things up. Otherwise, you're going to do a series of different plots, and you could probably just copy and paste stuff for the plots and make some changes. Are there any questions about this? Do you have a good picture of like what this is supposed to represent in nature? Yeah.
I just wanted to note that there's no hints for the exercise.
Yeah, there's no hints yet. I will maybe put some up as they're needed, but at least in the past, people have been able to kind of proceed through this without too much need for hints. So, but yeah, as questions come up, I can add things to the hints. For the moment, it's just empty. But any other questions? So if not, go ahead and get started. If you see any kind of typographical errors or any other problems in the exercise, let me know. And if you're using the CSC note